Good. Okay. So today I'm going to be talking a little bit about some computational geometry methods that have been useful for me and for others in quantum gravity. In particular, I'll be focusing on a few specific approaches to quantum gravity. Not all of them involve discrete geometry, which is what I'll be focusing on today. So I'll sort of get into some of the details about what that means, how we actually do experiments, and what some of the relevant research questions are. So just to give a brief overview of some of the questions that we're trying to think about, there are two main approaches to discrete quantum gravity. And by approaches, I don't mean something like, thin foams or causal sets or things like that. What I mean is you can think of things from a top-down view, or you can think of things from a bottom-up view. So the top-down view is really saying, how do I discretize a particular geometric space? What structures am I going to use? What are the relevant symmetries that I'm encoding in these structures? How much of the manifold am I going to keep? Am I going to be keeping information about metric and coordinates or just structural information? And then what are good discrete geometric observables, and what does good even mean? In this case, it's going to mean easy to measure, fast convergence, and renormalizable. Those properties are particularly important because in practice, even though certain expressions might involve arbitrarily large subgraphs that you need to identify, graph algorithms tend to be hard. And so identifying, some very obscure subgraph in a larger graph is in general not something that's feasible in simulation. So what I mean is simple local geometric quantities. And we want to have some idea of how they change with the scale that we're looking at in order to understand how things like curvature play a role. Now, there's also the inverse problem, which is the bottom-up approach. And this is saying, how do I recover a particular geometric space from the set of all discrete objects? And this is a very hard problem. In general, it's unsolved, but we are focusing on very specific examples, for instance, flat space or two-dimensional space, very, very much toy models. So some of the relevant things that we'll think about are, how do we restrict the focus to a particular dimension, a particular manifold, a particular topology, without really giving it the answer to begin with? And a key part of this is, like I said, understanding which subset of all discrete geometric objects, which subset of all discrete objects are also geometric, because we do not expect, for instance, all random graph structures to represent some manifold. Perhaps in some arbitrarily high dimension that may be true, but it's in general something that's not relevant physically. We are, of course, interested in 2 dimensions, 3 dimensions, 4 dimensions, not something like 100 dimensions. So in the context of quantum gravity, specifically, we're thinking about how does the continuum Lorentzian geometry emerge in discrete quantum gravity. So if we're starting with discrete Lorentzian structures, and we have perhaps some local rules about how they evolve or interact or how matter diffuses across them, we want to understand how do those local rules influence the structures that ultimately grow and evolve and ideally represent a manifold at the large scale. An important caveat to all of this is, of course, the scale. Since we are interested in simulating things, it's very important that these graphs are things that fit on computers. So like I mentioned above, good observables have fast convergence. So certain things that we've studied, such as the Ricci curvature, may converge at a logarithmic speed. And this is very problematic because it means that you might be able to measure it once in a graph at a certain point, but it's not something where you can measure it, over here and over there and at a third place and compare them simply because the amount of information that's needed is too great. So we'll get into a little bit of this later. So let me give you an outline. This is going to be broken up into 3 parts. Each part will introduce some ideas, and then it will be followed by about a 20-minute exercise where you can do some hands-on coding and play with some of these algorithms. So to start out, I'm going to introduce what discrete geometric structures we're talking about. In particular, I'm going to focus on sets, graphs, and simplicial complexes. Then I'm going to turn the focus to random geometric graphs, which is sort of the standard way to discretize a geometric manifold. And then I'll give another sort of view or take on things from the bottom-up picture, which is how to recover geometry from order theory, which is inherently non-geometric. There's a lot of interesting open problems there. In the second part, I'll go over a little bit some observables, how they converge, for instance, what geodesic paths look like, what cycles look like in the graph, what the path length distribution looks like, and why that's important, as well as, of course, the Ricci curvature, which is perhaps the most important observable. And then in the final part, I'll talk a little bit about the statistical physics of random graphs, how we construct ensembles of these things, how we measure the energy or the action of a graph, what a function of a graph looks like. And then from that, talk a little bit about manifold reconstruction and comparing ensembles of graphs. Okay. So the simplest discretization that we can consider, of course, is just a point cloud. So in this case, we're saying, let's look at a compact region of a differential manifold with some arbitrary Riemannian or Lorentzian metric. What we're going to do here is we're going to sample coordinates within the region uniformly with respect to some metric tensor that we've chosen. So for instance, if we're just doing flat space, then that means you're uniformly sampling within some region. Now, typically this region is going to be something that's nice to work with, such as a box or a diamond or a ball, but it's also motivated by physical things. So in the Lorentzian case, we might be interested in understanding how to discretize, for instance, the inside of a black hole. And that has a natural null boundary. And so that's one good example of a compact region where the boundary is, in fact, something that's physical. So this stochastic process that we're using is called the Poisson point process. And what this says is that in any given volume that you pick within your larger region, then the expected number of points in that volume is going to be a Poisson random variable. So what that means is that for 2 non-overlapping regions of your manifold or your discrete structures that you're looking at, they're going to be statistically independent. And this is a very important property. What it means is that the measure of your variables is going to be invariant under the symmetries of the metric. So for instance, if you do translation, or you do rotation, or you do boosts, this distribution is not going to change. So even though on the large scale, for instance, if you do a boost, you might see some drastic shift of your overall region of what the boundaries look like. But if you zoom in, the distribution is not going to look any different. So this is very important because, for instance, if you just used a regular lattice, for instance, like is done in lattice QCD, then the structure of it would not be invariant under boost. You'd end up with correlations. So an important feature that we already have is this discreteness scale. And so this is, I've written here, this L variable, which is rho to the -1/d, where rho is your sprinkling density, meaning the number of points in a particular volume, and this d is just the dimension. So for data structures here, we're just looking at basically a vector of coordinates. So this would be maybe n times d doubles. So it's really pretty straightforward, not very memory intensive, not very computationally intensive to generate, except for the fact that you're using random numbers. So that's really the bottleneck. And the complexity of this is order n. So where we might see this, for instance, is if we're looking at galaxy clusters or filaments. And in this case, for instance, in large-scale simulations or even observations, we might see pairwise distances between galaxies. And we want some way to understand how we can characterize the geometric structure, despite the fact that gravity is an infinite range force. And so, if you really think about it, you have this all-to-all connection, but not all connections are really equal. And it doesn't really tell you anything about the geometric structure if you just consider some fully connected graph. I'll come back to this in a moment to explain how you deal with that using higher order structures. So if we think about now graphs, well, a manifold is a union of open balls in Riemannian space or diamonds in Lorentzian space. So those are the topological bases. So what we're going to do is define some characteristic length scale, which is going to be a connection radius. And this should be much larger than your discreteness scale. Otherwise, you will not have a percolated graph. You'll have many components. It will not really represent any connected space. So this is an important feature that we want to think about. So what we do is we say, given our point cloud of coordinates, for every pair of points, we look at the distance function given by the metric. And if it's less than some cutoff scale r, then we're going to say that the two neighborhoods overlap. Hence, they get a relation between that pair. So for Lorentzian metrics in particular, this characteristic scale is just 0. Now, this seems a little bit odd at first until we look at what the metric is telling us. For Lorentzian metrics, we have one negative eigenvalue. And what that means is that you end up with this preferred direction, which we call the time direction. And ultimately, you can divide geodesics into two classes of time-like and space-like. And this simply means that everything that's causally connected is going to have negative distance, and everything that is not connected will have positive distance, or vice versa, depending on how you choose to write the signature of the metric. But the point is, the cutoff happens to be 0 just based on the geometry of the metric. So after considering all pairs, the resulting discrete structure is going to be what's called a random geometric graph. This is the standard way to discretize a geometric manifold. In particular, this object is important because it is what's called the skeleton of a simplicial complex, in particular the Vitoris-Rips complex, and it has been shown that this object is homotopy equivalent to the manifold, meaning it contains all of the properties up to some diffeomorphism of the original manifold. So these objects are really interesting to study. On the Lorentzian side, these random geometric graphs are called causal sets, and this forms one of the main approaches to discrete quantum gravity. Causal set theory is particularly interesting because it's the closest to discrete geometry. So if we're really thinking about how do we get a continuous, smooth Lorentzian manifold from some fundamental building blocks, this is one of the ways that people do it. Now, there are other ways that involve discrete structures, but I would argue that they are less connected to what's called geometric reconstruction, where we're trying to actually look at how you recover continuous observables, geometric quantities from the discrete ones. So it's a very appealing theory in the sense that it's requires very little. You're just looking at graphs. So if this cutoff scale R, if the ratio of that to the discreteness scale goes to infinity as the number of nodes goes to infinity, then we say the graph is dense. What this means is that if we look at a sequence of graphs, since we're interested in the graph limit, then that graph will be called dense if the number of connections becomes infinite. Now, I guess I should suppose, or I should say why we want to suppose that we look at this n to infinity limit. Well, there's a debate on whether or not that limit is actually important. Because on one hand, we want to understand, do these observables converge? Specifically, how does a finite set of points in the infinite limit end up looking something like a manifold? On the other hand, in causal set theory, one of the key axioms of the theory is that space-time is fundamentally built of discrete building blocks. And this discreteness scale, L, is the Planck scale, or something near there. And so in that case, you could argue that the theory is proposing that space-time is in fact built of a finite number of building blocks. The n is finite, but very, very large. So it's a bit of a nuanced point, but it's still important. So if the mean number of connections, on the other hand, remains constant, if that ratio goes to a constant instead of infinity, then we call the graph sparse. And so this is what you might think of as a triangulation or some mesh on some surface. And the difference between these types of graphs is very important because the observables, the discrete observables, many converge in the dense case, but do not converge in the sparse case. Or if they do converge in the sparse case, it will be at a much slower rate. And so it's very hard to deal with these types of graphs. So the last bit here for data structures, we're just going to use an adjacency matrix or an edge list. So constructing this is going to be an order n squared procedure because you're considering pairs of points. So in the examples that will follow, we will just consider an adjacency matrix, just to be clear. So the final discretization of a manifold that I'll consider is a simplicial complex. And so this is sort of the next level up from the path that we've been taking. So, well, of course, in a graph, we say if two neighborhoods overlap, we're going to draw an edge between them. Now, if three neighborhoods mutually overlap, then we're going to draw a face, like a triangular face. And so we can do this for higher and higher order groups. And what we see is that a k-click in the graph, meaning a set of k nodes which are mutually all connected, will give a k-1 dimensional facet. So you end up with not only polyhedrons, but higher dimensional things as well. And so this really is an interesting area of study. The simplicial complexes, for instance, form the basis for two approaches to quantum gravity. And these are the Euclidean and causal dynamical triangulations. And in these cases, you're not considering all higher dimensional facets. You're really just considering polyhedra. But it's slightly different from the causal set approach in the sense that you're not discretizing a manifold. You are looking at how to glue these things together such that you end up with Lorentzian structures. So it's a bottom-up approach. In the Euclidean case, there have been many difficulties because there has been really no geometric phase that has been found for any set of parameters. So that area of study is dwindling a little bit. In the causal dynamical triangulations approach, people say, let's look at simplicial complexes, but with a specific foliation that leads to causal structure. So that's put in by hand. And it looks so far like there is some phase that looks like de Sitter, which would be interesting to study further. But unlike with causal sets, well, I guess the same as causal sets, in both cases, renormalization is a very, very active area of research. And so this is important because we might have something that looks foamy and random on small scales. And then as you coarse grain it, you end up with something that looks smoother. And this is an expected feature of quantum gravity, which makes it more difficult, I think, to start from the bottom-up approach than the top-down approach. So for the data structures here, we're looking at something called a simplex tree. I'm not going to go any further into simplicial complexes, so I won't discuss that. But the reason I wanted to bring this up is because for this example I gave earlier about point clouds and galaxies, one of the things that you would do is if you're doing a topological data analysis, you can build simplicial complexes by looking at a scanning over characteristic length scale. So you start with r equals 0 and look at the simplicial complex that's formed from that. Of course, it's nothing. And then as r increases, you're going to end up with higher and higher order facets in your simplicial complex. And so if you look at those features which persist over the largest number of length scales, you're able to extract some topological information and determine, for instance, is this a filament? Is it a spherical cluster? How many holes is it? Is it a donut? Just sort of looking at the homology of these objects. Okay, so I'm going to turn back now to random geometric graphs and give some specific examples. So how do we discretize curved spacetime? Well, let's look at 1 + 1 dimensional de Sitter spacetime. De Sitter, of course, is interesting because it represents the exponential inflationary period in the early universe. It also represents the inflationary period that we see at late times in the universe. So it's a nice toy model to play with. So what we're going to do, I'll just give a little bit of basic differential geometry here. We write the line element out, and what this is all based on is this metric tensor G here. And so we can write this out as minus dt squared plus cosh squared d theta squared. And what this is describing is a de Sitter hyperboloid. So the spatial slices, which are circles, are going to expand exponentially as time increases. The volume form that corresponds to this is going to give a joint probability measure on the variables t and theta. So you can see here, if I write this out, then this joint probability measure is really determined by the square root of the determinant of your metric tensor. So it's written here just as p of t and theta is equal to cosh of t, the time. So because this is a product, which is a trivial product in this case, p of t times p of theta, it's separable, and we can sample points from those two distributions independently. If they were not decomposable as a product, then you would have to use the marginal probability distribution and then the conditional probability distribution, which is a little bit more work, but computationally, it's definitely feasible. You just end up using bisection methods. So if we write out these normalized probability distributions with respect to some boundaries that we'll look at in the next slide, we end up, for instance, sampling from a cosh distribution and from a uniform distribution over 1 over 2 pi. Like I said before, if this distance is negative, we're going to say the points are time-like separated. In other words, they're causally connected. Otherwise, they are space-like separated. What we're going to do is check to see if the light cones are going to overlap for this region. Okay, so let's look at a specific example. So if we consider a slab of the upper half of the de Sitter hyperboloid bounded from t equals 0 to t equals some characteristic cutoff and theta between 0 and 2 pi, we end up with a region that looks like this. Now what we're going to do is sprinkle points using a +1 point process on this region, and we end up with a point cloud that looks like this. So what I've done here is I've drawn it from a top-down view using a Poincaré representation. And all this says is that the t variable is written as the radius. So the throat here, this lowest point on the de Sitter manifold, which is a circle, is going to be mapped to the center of the circle here. So you can see there's an exponential distribution in the radial direction and what looks like a uniform distribution in the angular direction. Now what we do is we draw a light cone for a pair of points. So for instance, in this example, this pair does overlap, and so we see that they are causally connected. Now this type of diagram is actually very useful because it tells you several things. First of all, it tells you that no matter where you are in this space-time, you can see that your light cone is going to ultimately end up looking like it's perpendicular to this boundary. It's not going to expand to cover the entire boundary. So this is what we call our observable universe. What it means is that if you are at this lower point here, this yellow circle, and you're traveling at the speed of light in any direction, then the farthest you can get is the boundary of this shaded region. You can never, ever get to most of the universe, in fact. At the same time, you can see that you can only see a finite portion of the causal past, again, no matter where you are. This is a feature of de Sitter with singularities. For instance, the one that represents our universe, we do expect that it would be slightly different. So we do this for all pairs of points, and we see that what one realization of the graph looks like here. It looks sort of very spiky and pointy, and what you're seeing here is reflective of the light cone. So if you're looking for instance, a path that gets you from one side of the circle to the other, it's going to look like a zigzag path, and that will just be sort of going along these light cones. So let's take a step back and think about the precise mathematical condition for linking. Well, what I haven't told you is that there is a simpler way to do this. And it's important that you use the right coordinates to do this procedure. You can use other coordinates, but computationally, you'll be wasting a lot of cycles. So we're going to use this conformal time, eta, and it's related to the original time, the cosmological time, t, using, by this equation, cosh t equals secant of eta. The reason this is important is because in this coordinate system, the light cones are going to be straight lines. So we're really just looking at overlapping diamonds. Very simple. The metric then is factorized in this form, where the conformal factor, secant squared eta, is written out front here. And the thing in the parentheses is just a flat metric. So this is nice because it means that sprinkling is also much easier. So we say that if the difference in the angle for a pair of points is less than the difference in conformal time for a pair of points, then we link them. It's as straightforward as that. So because of periodic boundary conditions, this is the expression that we end up for the two theta coordinates. And then for the time coordinates, we're just going to end up using this expression here. If you had sampled using conformal time to begin with, then this would just be a simple absolute value of the difference. So in general, these conformally flat random geometric graphs are much easier to generate because they can be factorized in this way. So what I haven't mentioned is that there are some easy methods to optimize this. Does somebody have a question? Oh, okay. There are some easy methods to optimize this. In particular, if you're working with parallel algorithms, you'll notice that these can all be done independently, effectively. So all of your points are sampled independently because they are Poisson random variables. So that can all be done independently so long as your random number generator is thread safe. And then this linking procedure can also be done independently because the connection probability for a pair of points is not going to depend on any other pair of points. It's only dependent on their coordinates. So this is something, because it's a matrix operation, is actually very well suited for CUDA and GPU computing. Okay, so the last thing I'll introduce before we get into some exercises is order theory. So this is actually very important in two-dimensional quantum gravity. So because Lorentzian random geometric graphs are directed and acyclic, they have an equivalent representation as partially ordered sets. And these are just sets where for every pair of elements, either A precedes B or B precedes A, or neither of them are related. And so because of that property, we have what's called a natural labeling, which says that for a pair of nodes in your graph or elements in your partially ordered set, if I precedes J, then in their labeling lambda, then lambda of I is less than lambda of J.
So I'm not. There's something called Cisco. And I just downloaded it.
So one example of a natural labeling, for instance, is the time coordinate or even conformal time that we used in the previous section. But in general, when we talk about natural labelings, we're talking about an integer sequence or some permutation over the integers. So the set of all natural labelings for a particular partial order or Lorentzian RGG is going to form the linear extensions of that graph. So for instance, for a diamond, you might use the sequences 1, 2, 3, 4 and 1, 3, 2, 4. And what that indicates is that this element 1 is going to be at the base of the diamond. It is going to precede all of the other elements in both of these orderings. 2 and 3 come in opposite orderings in these two, and so that represents this disconnected pair in the middle of the diamond. So you would not have a link between elements 2 and 3 because of this. However, you do have a link between 2 and 4 and 3 and 4 because in both of these orderings, that same order is there. So in some sense, it's this natural labeling is a bijection to the integers that's order preserving. So the 2D orders are graphs represented by intersections of at most 2 linear extensions. And we say that as in this diamond example, if the order relation exists in both pairs, then you add the corresponding link between those nodes in the graph. And this is one way to construct, for instance, some ensemble of geometric graphs. So one very important result is that a uniform measure over the 2D orders is peaked around sprinklings into 2D Minkowski diamonds. This is very interesting. Now, why is this? One way to see this is that these order variables, whether they're integers or random numbers between 0 and 1, act as light cone coordinates. So if you consider a coordinate system rotated by 45 degrees, so that you have two axes which go at 45-degree angles, then if you place points according to, if these are your x coordinates and these are your y coordinates, for instance, or u and b in light cone coordinates, then this gives you a 2D order. And I'll show a picture of this on the next slide. But before I show that, I want to mention that it's unsolved what this relationship is in higher dimensions. And even measuring the order dimension, meaning the number of linear extensions that you need to construct a particular graph or partial order, for d greater than 2, it's NP complete. So it's a very hard problem. But this is perhaps one of the most interesting areas of research, in my opinion, because it really connects something fundamental and mathematical to something which is a geometric manifold. So here are some examples of 2D orders. So like I said before, you have these integer numbers, which gives your light cone coordinates on these axes. And as I was showing before, you can draw these light cone diamonds, which basically says that if another node is to the future of it within its light cone, then it adds a link. So for instance, here you have a set of all related elements. In the middle, you have a set of all unrelated elements. And then you have something which is, has a richer structure in this last example. And so to yeah, like I said, the two linear extensions of the light cone coordinates. And so it's really rather straightforward in 2 dimensions. But for higher dimension, it's not so easy because, as you might be able to see, if you added a third axis to this, you'd end up with a cubic lattice. And we know that light cones intersect as circles. And so that's a bit of a problem. So it's not quite the same. So for some algorithms for order theory. So what is the relationship between the ensembles of Lorentzian sprinklings and the ensembles of D orders? This is a key question. So the way that you generate these orders or study this problem is you might generate some number of vectors of length n, initialize them however you want, perhaps 1 through n, and then you might do some Fisher-Yates shuffle, which is a random shuffle on your vector, and this gives a random permutation. So this would be an example of how to get a random D order. So when an order relation agrees among all of these orders, you add it to the graph. You might now do some Monte Carlo simulation where you swap adjacent pairs or adjacent subsets of your order, and this would give you some way to study the sample space of the D orders. The height and the width of the graph, interestingly, corresponds to the length of the longest ascending or descending sequence present in all orders. So this is another example of where order theory plays a role directly in geometric properties. So now I want to turn to the first exercise. There are a few parts here, and I have some solutions, which I'll post in a little bit. So first, I'm going to ask you to construct a 3D Minkowski diamond, similar to what we discussed earlier, using 500 points. So what this means, you can use rejection sampling, sprinkle into a box, and reject points that are outside of your pair of cones. For each pair, you link them using this condition that we talked about. This former one is going to be just the 2D Euclidean distance for your pairs of points x and y. And then I want you to look at the mean number of relations per node and see is this value correlated with time coordinate, y or y not. And then finally, compare this to some of the graphs that you get from random 3D orders of the same size. And there are some instructions for how to do that here. Okay. I'll give you about 15 minutes to do this. Okay, I'm going to continue on with the slides now, and we can come back to the exercises at the next break. So for the next portion, I want to talk about, now that we've introduced the structures that we're interested in, what are some observables that we're going to look at on these structures, and what are the rates of convergence for these observables to their expectation values in the continuum. So there are, in fact, a lot of geometric quantities that we're able to measure. For instance, the dimension has a handful of estimators that we'll look at. We can look at the geodesic distance using either weighted manifold distances or unweighted distances, as you would see just in a unweighted graph where edge lengths are all equal to 1. A key interesting feature here is that for Riemannian graphs, geodesic is going to correspond to the shortest path between 2 points, whereas for a Lorentzian graph, it's going to correspond to the longest path. And the reason for that is because in Lorentzian geometry, we have long-range causal connections due to the light cone structure. So a shortest path is simply going to bounce off the corner of a light cone and go straight from A to B if those 2 points are causally connected. Whereas the longest path is going to do some zigzagging up the middle of your causal diamond. We can also look at simple properties like the width, the height, cardinality of your set, which is going to give some information about the volume. There's a lot of interesting study in convex hull problems where we're interested in looking at boundary geometry. In fact, this is a very difficult problem for random graphs because most of what you're building and representing on the computer is going to be in the bulk. And so to measure something that's just on the boundary means that your bulk already has to be quite large. And because you need many realizations, in fact, and the convergence is slower on boundaries, it's actually very difficult to measure extrinsic curvature and boundary volumes. We can also measure the Ricci curvature both in the Riemannian and the Lorentzian setting, although they're done in very different ways, and I'll get to that in a moment. There are also some interesting pre-geometric statistical quantities that are typically studied just as a means of comparing graph ensembles, really. So we can look at the ordering fraction, which is the number of relations present in the graph compared to the total number, and choose 2. We can look at the degree distribution, which is basically the distribution of the mean number of connections that each node has. And although that's less important, I would argue, in the geometric setting compared to general graph theory, simply because it's so heavily dependent on the region that you choose to study. So it's not going to tell you information really about the underlying manifold. Another interesting property, particularly for Riemannian graphs, is the clustering, and this is the fraction of triangles that are present in the system. The reason that's important is because it's been shown that for random geometric graphs that are Riemannian and have a percolation of triangles in the graph, these are necessarily geometric in the sense that they're similar to sprinklings, which have the same average clustering and degree distribution. So that's an important observable for the Riemannian case. We can also look at spectral geometry. This simply means that we're looking at the spectrum of the adjacency matrix, of the Dirac operator on such graphs, the D'Alembert. Basically, there's a whole other field of study of spectral geometry, so I don't really want to focus too much on that. So let's take a look at dimension. In general, dimension estimation is a hard problem, so we use estimators. And typically, these estimators are going to make certain assumptions. For instance, that at small scales, meaning in local neighborhoods, our graphs are going to correspond to flat manifolds. So this is motivated by the idea that for any nice geometric smooth manifold, at small enough scales, it's going to look like a flat surface, whether it's Euclidean or Minkowski. And so we use this assumption then to test local regions of our graph to see, do they look flat, for instance, or as you look at larger and larger regions over different length scales, how does it start to pick up curvature information? So for instance, the Hausdorff dimension is going to look at the scaling of ball volumes, and this is something that we use in Riemannian manifolds. So if we say that the number of points is roughly equal to the radius of some neighborhood to the power of the dimension, then we can use this as a way to estimate the dimension by looking at the number of points in neighborhoods using graph distance. So in this case, a neighborhood of a certain point will be, for instance, all points which are at most 3 hops away or 5 hops away. And that would be your R value. So as those balls get larger and larger, it should become more accurate. We can also look at the spectral dimension, which is nice because it's something that is easily applicable, generalizable to Lorentzian or Riemannian graphs. And here we're just looking at the return time for a random walk on these graphs. Now, a random walk on a graph is a very straightforward procedure. You're just starting at some point. You're picking a random neighbor to hop to at each time, and you're just repeating this procedure infinitely. Now, for the Lorentzian case, an important caveat, of course, is that there's this implicit direction in the graph, meaning causal direction is one way, it's not two-way. However, if we have our graph labeled using one of these natural labelings, what this means is that our adjacency matrix can be written in upper triangular form. It also means that based on the way that we represent our data structures on the computer, those directions can be implied by the indices of our nodes. So that's why the labeling is actually a very important feature. So for a random walk in Lorentzian graphs, we are going to consider both future and past directions when we're looking at the spectral dimension. There's also this Myrheim-Meyer dimension, which is exclusive to Lorentzian manifolds. And what this is doing is it's studying the fraction of relations that you would see in a Minkowski diamond. So given a larger general Lorentzian random geometric graph, you can always choose a diamond subset by picking a pair of points and looking at their looking at their intersection. So it's the future of one point intersected with the past of a second point. So this expression is going to be exact for Minkowski diamonds. It will not be exact for general graphs. However, it is a good way to distinguish between something which you believe is close to geometric or pre-geometric versus something which is totally random, very high dimensional, not connected well, not geometric. So it's useful for more than estimating dimension, because typically things which are non-geometric end up telling you that they have very, very high dimension on the order of n. Of course, to be certain, for any estimator or for any observable, we're going to use multiple estimators, take ensemble averages. And so this is why these things do tend to take a little bit of time computationally, is because we need efficient implementations to get very large neighborhoods in the Hausdorff case, or very long random walks or large diamonds. So now let's take a look at geodesic distance. So in the Riemannian case, the shortest paths are geodesic. So what you're going to use, I mean, there's a whole host of pathfinding algorithms for graphs. This is not something that's unique for quantum gravity at all. It's something that's, there are many, many examples online of different ways, different implementations. It's a lot of fun to take a look at all of the different variants and how they improve on one another. So what we're going to be considering in particular for discrete geometry, if we're using unweighted distances, meaning we're not keeping the metric information from our manifold, we're just creating the graph and basically throwing away the coordinates and the distances, then we would use something like a breadth-first search algorithm. And so what this is doing is it's starting at a particular source. You have some particular target in mind, perhaps represented by some labeling number. And what you're going to do is, for each neighbor of your root node, you're going to assign it some distance 1. For each of their neighbors, you'll find distance 2. For each of their neighbors, you'll find distance 3. And you'll just keep going on and on until you end up at your target node, and you'll have the distance for it. So it's pretty straightforward. For weighted distances, it's a little bit more work. The weighted shortest path in a graph is an extremely well-studied problem. You might be familiar with GPS systems, which if you're considering driving across the country and you need to know the shortest path, then you might see a GPS system use, for instance, the A-star algorithm or Dijkstra's algorithm in order to do that. And we'll go into that in a little bit more focus on the next slide. One key observable that we're interested in is what's called the stretch. And this is the ratio between the graph distance and the manifold geodesic distance. So one way to see that, sort of how to visualize that, is if you are driving across the country and you have to take some series of roads and you add up the miles that you drive, you'll see that it exceeds the distance that you would have traveled if you could fly. And as the discreteness scale gets smaller and smaller, meaning as you add more intersections, as you add more roads, it's going to approach that shortest path distance. And so the stretch is in one way a good way to measure how close your geodesics are to convergence. In the Lorentzian case, you're going to do slightly opposite things. You're going to be looking at longest paths, which corresponds to time-like geodesics. Now, I'm specifically not mentioning space-like geodesics because, first of all, they're not really physical. Second of all, we're more interested in spatial geometry, for instance, constructing Riemannian graphs from hypersurfaces of Lorentzian graphs. But those are not space-like geodesics in the larger Lorentzian manifold. So we typically just restrict our focus to time-like geodesics. For these, we're going to use a depth-first search algorithm. So it's similar to breadth-first search, except instead of starting at a certain point and looking at all of its neighbors, and then looking at all of their neighbors, what you're going to do is pick a particular neighbor, and you're going to go as deep as you can in the graph, and then you're going to iterate over all possible ways that you can traverse the graph. In this case, the way that you have labeled the graph is important because you want to always look at, you want your starting point to be one of these root nodes, which would be like something from the very early universe. And you typically want your target to be something at the top of the graph, which would correspond to something at late times. Yeah, in the depth first search, you're going to be looking for the longest path. So an important result here, of course, is that in Minkowski spacetime, at least, it has been proven that the longest path in units of the discreteness scale is directly proportional to the time-like geodesic distance. And this proportionality constant depends only on the dimension. It has been solved exactly in 2 dimensions, but there is no known exact expression in higher dimensions. For curved spaces, a similar expression can be constructed. It's a little bit more work. Yeah. So let's look a little bit more closely at Dijkstra's algorithm here. So what we're going to do is take our full set of nodes and we divide them into 3 categories. They're either visited, they're in the frontier set, or they're unvisited. And so maybe just from these names, you can sort of see how we're going to traverse the graph. First of all, we're going to set the distance for all nodes to infinity. And then we're going to set the distance for our source node equal to 0. So the distance, this distance vector is going to indicate how far we are from our source. And the others are set to infinity simply because they have not been reached from the source yet. So we're going to pick some node I in the frontier set, which initially is going to just be our source node. And we're going to pick the one with the smallest distance value. If it's the target, then we're done. But otherwise, we're going to look at each neighbor, and we're going to say that the distance that we assign to it is going to be the minimum of the distance from the current node plus that Dij, which is our manifold distance. So it's the true geodesic distance between a pair of nodes which are related in the graph. Now we're going to move that node that we were looking at from the frontier set to the visited set, and we're going to add all unvisited neighbors that have been looked at newly into this frontier set. And then after that, we repeat. So it's a fairly straightforward procedure. We're just iterating one by one, always choosing the node which is closest to our source, but still in our frontier set. And so this creates sort of like a circle around our source, and it spreads at a uniform rate. And you can visualize this pretty easily. So one thing to think about is how you would change this for multiple targets. In this case, you would want to look at the A-star algorithm, where you're able to have some sort of heuristic which tells you how close you are to the destination as well. And so rather than just picking the node which is the minimum distance from the source, you're looking at the node which is the minimum distance from the source plus the distance estimated to the destination. So if you have a good heuristic, for instance, an underlying geodesic distance that you already know, then it will be more efficient. So one of the more interesting observables is the Ricci curvature. So in the Riemannian case, we're going to use this expression called the Olivier-Ricci curvature. And there are a handful of different graph curvature metrics, but this is the one which converges to the Ricci curvature in Riemannian geometric graphs. So what we're going to look at is this statistical quantity called the Wasserstein metric. And what this does is it gives you some estimate of the distance between statistical distributions. So if you consider, for instance, some uniform distribution on the nearest neighbors of a particular point, and another uniform distribution on the nearest neighbors of a separate point in your graph, then you have two discrete distributions. And this metric is going to tell you the cost of parallel transport of these distributions across the graph. This will be based on the graph distances and also the graph structure. So specifically what it's doing is it's identifying the minimum distance and the joint probability measure given to marginal distributions on the neighborhoods. Typically, the way we set this up is such that the distance between the 2 points is equal to the radius of the neighborhood. So what we're doing is we're considering two uniform distributions on delta balls, x and y. We're considering this uniform distribution, mx is 1 over the sides of the neighborhood of x, and y is 1 over the sides of the neighborhood of y, so they're normalized. And then really the bottleneck for this method is constructing this discrete distance matrix. And so that's really why I wanted to talk about this Dijkstra algorithm, is because it can be very, very expensive if you have, suppose you have a graph and these two neighborhoods are each 25 or 30,000 nodes. And for two pairs, sorry, for this pair of neighborhood, for every pair of points, you need to figure out what the shortest distance in the graph is going to be. That's a very expensive operation. Once you have this matrix, though, you're going to solve this convex optimization problem. So you minimize this variable W, which is the Wasserstein distance, and you're going to end up solving for W, but also this rho variable. This rho is called the transport plan. What it's going to tell you is the amount of the mass, the probability mass, that moves from neighbor I of your source to neighbor J of your destination. Okay, so it's subject to these constraints here, which are just normalization constraints and conservation of probability. So typically for this last point, there are software packages that will do this for you. It's not something that you would implement on your own. So just to give you a picture of what this looks like, once you have this Wasserstein distance, you can calculate the curvature first looking at the Olivier curvature, which
Yes, it works.
Okay, I think maybe my headphones just died. Okay, so what I wanted to focus on here is that the number of nodes you need in your graph is actually quite large if you want to measure the curvature. And this is why I was mentioning that this is not something where you can do it for many different non-overlapping neighborhoods, because here you're looking at graph sizes which are at least, say, 2 to the 12, really closer to 2 to the 14. So you're looking at least 10,000 nodes. More likely, you're looking at around 50,000 nodes just for really a single estimate of curvature in a single area. And so the way that breaks down is that you end up with sort of two neighborhoods, which each are comprised by half of the nodes in the graph. and you end up with some very slow convergence at a logarithmic rate. So here I've given 3 examples. One is the torus, which has flat curvature. One is the sphere, which has positive curvature. And the last is this Bolzano surface, which is like a double donut. It has a negative curvature. So you can see it's not something that's, at least at the present time, not easily able to be used as the kernel, for instance, for Monte Carlo simulations, where you might want to base the weight on a graph based on integrated curvature or the action, for instance. So now I'll point you guys to exercise 2. It looks like if time runs out, this might be the last bit. What we're going to do is construct a 2D Euclidean random geometric graph. This is a straightforward exercise where you're just sprinkling into a unit square and connecting points which are below some threshold. And then estimate the Hausdorff dimension. So in order to do this, you need to figure out how can you identify neighborhoods for given points of different radii. Then maybe estimate the clustering coefficient, which is the fraction of number of triangles in the graph. And see maybe how this generalizes to higher order cycles. So the number of cycles of length n is going to be one of your characteristic graph features that you might be interested in. It's a very rich observable. Then estimate the length of the diagonal by measuring the longest path and multiplying it by the discreteness scale. And finally, for a pair of nodes, divide the shortest weighted path by the Euclidean distance in order to get an estimate for the stretch and see what sizes are necessary. So I'll give you a few minutes to look at that. Just to very quickly go over part 3, and then we can leave the last exercise for later. So the last bit is just putting this all together to talk about statistical physics of random graphs. So we can form a Gibbs measure on graphs if we use certain forms for the energy or the action of this graph. So as an example, consider the Hamiltonian of a graph, which takes 2 graph observables, the number of nodes in the graph, and the number of relations in the graph. So again, these are label invariant quantities, which are going to go into your Hamiltonian. And then you have 2 couplings A and B. You have 2 couplings A and B, and you're going to use this to assign some energy or action to your graph. In the Riemannian case, typically we talk about the energy of graphs. In the Lorentzian case, we typically talk about the action of graphs, and this is just for historical reasons. But really, we're doing the same thing by looking at this partition function here, which is going to be a function of your temperature value. And then you're going to sum over all graphs in some ensemble and use this Boltzmann weight here. So for the Lorentzian case, the way that this is related is you're looking at this analytic continuation of this beta parameter so that you end up in the continuum limit getting some estimate on this gravitational partition function. So in the continuum, of course, it's very difficult to understand what we mean when we're integrating over all metrics, because you have to consider all metrics with perhaps certain symmetries, but also all topologies, all sorts of weird fluctuations at small scales. It's not clear how to deal with this, whereas in the discrete setting, it's very simple. You're just looking at some ensemble of graphs. The key unsolved thing here is which choice of Hamiltonian or action is going to lead to the right measure. Some important features that we're looking for when we construct something like this is that the dynamics produces a second order phase transition with at least 2 phases. One should be geometric, one should be random. So this roughly corresponds to low temperature and high temperature. We are also looking for scale-free structure at large n at the critical point. And so this is where we expect our large manifold-like structures to emerge. We also expect there to be some renormalization flow for the coefficients. And this is an interesting unsolved problem. And the best way that we are able to get at it is to simulate the same thing at many different sizes. Another interesting bit here is that the dimension should be selected by the dynamics, and this is actually a very difficult problem because with graphs, you're able to have all sorts of non-local connections if you choose to allow them. At the same time, for Lorentzian spaces, we know that there should be some non-local connections due to these long-range connections when you're close to the light cone. So it's a challenging problem, and it's much more difficult to do something like this than if you're simulating an Ising model, because you have these long-range connections. So everything that you're measuring is going to be, in some sense, global, because when you change graph structure, it may have very important consequences. For instance, if you take a link out of a Lorentzian graph, it may also delete many relations which are transitively imposed by that link. So for Lorentzian graphs, we're going to use what's called the Benincasa-Dautker action. So we're looking at the statistical ensemble here. We're picking an action corresponding to a specific dimension. So this is an important part about the causal set approach, is that you have to presuppose what your dimension is going to be. And the cost of a particular graph is going to be an alternating series, which is a function of the number of nodes, as well as these three numbers, n1, n2, and n3. And what those are telling you, those three numbers, is going to be the abundance of various types of subgraphs in your larger system. So you're going to count, for instance, how many links are there? How many of these objects are there, which are called two chains? How many of these, the three chains and the diamonds? And so on and so forth. You can construct higher order versions of this, either for higher dimensions, or if you're trying to get better estimates, you can extend the alternating series. There is, in fact, a family of these expressions which use more and more terms, but this is the one which uses the minimum number of terms. So what this corresponds to algorithmically, if you have an adjacency matrix, if you want to measure the abundance of these, what you're going to do is take, for instance, rows I and j of your adjacency matrix. You're going to do a partial intersection, which is essentially multiplying those rows between columns I and j, and then summing. So it's a partial inner product. And the number that it spits out is going to tell you which of these subgraphs you're looking at. So now I'm just going to very quickly describe how you would do some sort of Monte Carlo simulation of this. You're going to pick some initial configuration, for instance, a random graph. It could be a sprinkling, it could be a d-order, it could be anything you can cook up. You're going to identify your ergodic update. So link addition or removal is the simplest, in particular in the Riemannian setting. In Lorentzian setting, it's not so simple. So I don't want to focus too much on that. We're going to choose a Hamiltonian for this. So, for instance, we can pick any linear function of subgraphs with some coefficients. And then we're going to accept an update with a probability given by this metropolis condition. What we're going to do is record the graph observables every sweep for at least 1,000 sweeps. In practice, you're going to want something at least 10,000. Unlike the Ising model, we need order n squared updates per sweep as opposed to order n updates per sweep. So this makes it actually very difficult to get to large n for these graphs. The reason for this is that in the Ising model, you only have n things that you can update. These are your spins on your lattice sites. Whereas for graphs, if you're playing with the links, if those are your free variables that can change, you really have order n squared. And so there's much richer structure there. At the end of this, we want to understand what are the properties of a typical configuration selected by the Hamiltonian. And do these properties change with beta? Is there some sort of phase transition? Do we expect a phase transition for a particular Hamiltonian based on some physical principles? So that would be very important. I've written a bit here about how to filter out correlated data. Basically, it's very important that once you do these simulations, you measure autocorrelations. And you have to do this for not just something like the energy of the action, many observables, because they will have different autocorrelation times. And so things which appear to be statistically independent might actually be correlated if you're looking at, for instance, the length of the longest path in a Lorentzian graph or the length of the shortest path, the longest, the diameter of the graph in the Riemannian case. This autocorrelation is going to be very large near critical points and at low temperatures, and this is the critical slowing down problem. So it's very difficult to get good samples in these regions, and this is something that is well studied in many areas of physics. I would recommend, if this is something you're interested in, you should look at advanced methods like parallel tempering and population annealing in order to decrease the autocorrelation. These are methods which have become popular in spin glasses and condensed matter physics, but they're increasingly relevant really in graph theory as well. I will skip this bit about geometric reconstruction. The only point is to say that once we do some sort of Monte Carlo simulation, we want to understand, we end up with some ensemble, which some measure over all of our graphs, and we want to understand how does that measure compare to the measure over graphs which originate from sprinklings, from specifically discretizing a particular manifold. Again, you have to pick a particular region, so that may also influence what you're doing. But you can you can filter that out by saying, for instance, in the Lorentzian setting, I'm going to do some sprinkling and then get rid of everything outside of the largest diamond. Or in the Riemannian case, you can similarly construct a ball, and that gives you some way to normalize for the choice of region. Yeah, so the last bit that I wanted to mention in exercise 3 is basically just do what we did in the previous exercises, except now you're constructing some Hamiltonian of your favorite graph observables. It can really be anything. And you end up with some coefficients that you're free to choose, some temperature parameter, and you can use this to do some Monte Carlo simulation and figure out, do you end up with geometric graphs? Do you end up with an interesting phase transition? Okay, so that's all.